I had a great weekend. It was really nice. What about you guys? I had 2 Thanksgiving dinners, so that was agreeable for me because it's kind of my favorite time of year. I love fall. I absolutely love fall. I adore it. And I love food. And I love seeing my family, like my big extended family. So we had not quite everyone. Now when on my mom's side, now when we get everyone together, I think it's about 40 people, and I think we had about 30. So that was pretty good. So that was nice. And then we did my in-laws, and that's a much smaller family, but I love getting to hang out with them. So yeah, it was nice. What about you? Do people do the Thanksgiving thing? Like, do we have turkey? Do we have no? You guys don't partake in white people feast? Because it's objectively a pretty boring meat, and I get that. But it's a good meal. It's a good meal, the Thanksgiving meal. I don't know. I like it. Yeah. The leftovers are the best part. That's an interesting thing, but it's true. Because now you can do sandwiches. You can make a nice soup. No soup. What? Ah.
Can you answer it?
Can I answer what? Yes. Yes, I can. There we go. That should be good. Anyway, yeah. And you guys got a long weekend. You also got Friday off. If you can imagine, while you were off having fun and gallivanting, we had to sit in meetings and for 75 minutes at a time, it was can you sit down and focus? Had to stay in one place. It was a paper and we were expected to fill out notes. It was hell. It was torture. Torture. Can you imagine? Can you imagine doing that to someone? Anyway, we'll move on. Quiet. This is totally different. Totally different. This is science class. Everyone knows. Staff meetings are supposed to be for socialization. English class is fun. History is for catching up on your sleep. Geography is for picking up girls. But chemistry, serious business. All right, so today we're going to look at our next functional group. This should be a quick lesson, which should then give you a bit of time at the end if you didn't get your homework done, of course, or your assignment done, which of course you should have. But if you didn't, you'll have a chance to get it finished up. So I took today's lesson and cut it down to just one more functional group. We're going to talk about carboxylic acids. Carboxylic acids. This is an organic acid. Remind me about Arrhenius theory. Remind me about the definition of an acid as you have learned it thus far. What can you tell me about acids? Yes?
Anything that gives H plus ion in water.
Very good. Anything that can release a hydrogen when, in what particular condition? When the molecule or when the atom or when the compound is aqueous, which means what? Dissolved in water. Good. So, our definition of an Arrhenius acid is something that releases H plus when dissolved in water. That's actually written right above. I'm literally rewriting what's in the black text.
Is H plus clean or dirty?
I don't know. Je ne sais pas. Does it look clean?
A lot of the stuff looks dirty.
Well, let's wash it. Thank you. You're the best. So when you dissolve something in water, if it releases an H plus. Now, interestingly, organic compounds are full of hydrogen, right? You think of an organic compound, and it's don't draw this. It's what would this be? What compound is this? Propane, covered in hydrogens. So will this act like an acid? It's full of hydrogens. I mean, this won't even dissolve in water, right? This is non-polar by definition. We could make it polar. We could add an OH group. What's that now? An alcohol. What's it called? Propane. Does this need a location on that alcohol?
No.
Ooh, I have a yes and a no. Should we arm wrestle?
Yes. I think yes.
You said no.
But now
You said no, and then I said arm wrestle. You're like, yes, okay, yes, whatever. You don't think you could beat him in an arm wrestle? I think you could beat him in an arm wrestle. There's one way to find out, though. Irrespective of all the chemistry, all in favor of them having an arm wrestle? All right, all opposed? All right, the yeas have it. All right, let's see. You can do this, Nana. You can do this.
I'm betting all
Okay.
that
All right, go.
Oh, yeah.
Carter, oh no! Okay, that was good. I was getting distracted. I was gonna say threatening things.
I didn't put any hours.
Sunena, thank you for being a good sport. I appreciate it. Kartik, well done.
I almost lost.
Those fingertip push-ups are helping you out and getting you buffed up. All right. So listen, this does have a hydrogen on it, but it has no acidic hydrogens. It has no hydrogen that can be released. Does that make sense? Just because something has a hydrogen doesn't mean that it will release it when it's dissolved in water. It would if it were an ionic compound, because then, of course, it would be made of an H plus ion. But this is not ionic. This is covalent, right? It's oxygen-hydrogen making a covalent bond. So in a carboxylic acid, what we basically need to do is we need to build a molecule that, given just a little nudge, will steal hydrogen's electron and thus release it as an H plus ion. Looking on the periodic table, what is going to be our best candidate for connecting to a hydrogen in a way that will want to steal it? Well, actually, we've already used it, because fluorine can't be, we couldn't have this. Don't draw this. We couldn't have carbon, then fluorine, then hydrogen. That would be our best bet, right? Because it's highly electronegative. But fluorine doesn't make two bonds. Fluorine only makes one. So actually, that carbon to oxygen to hydrogen, oxygen is the most electronegative thing. Don't draw this. Not yet. Don't worry. I'll tell you when. That's our most electronegative thing. It's giving us a dipole this way. In other words, it's saying it's really trying to take that electron from hydrogen, but it's not enough. But what if we put more oxygen here? Oxygen is highly electronegative. So if we put another oxygen here, that would put even more pressure on the electron from that hydrogen. Does that make sense? And that, in fact, is the structure we see. The way we can make a hydrogen acidic in an organic compound is to put an aldehyde and an alcohol on the same terminal carbon. And of course, the rest of the chain can just go here. We call that an R group, but that is just the rest of the chain. So if we have an aldehyde and an alcohol on the same terminal carbon, we refer to that as a carboxylic acid. And this hydrogen now has enough pressure on it that this is the acidic hydrogen, which is to say, this is the hydrogen that will get released when dissolved in water. This you can write down. Thank you. So in this configuration, and again, this doesn't happen for some random reason that you can't understand. You don't have to memorize this. There's a logic to it. And the logic is that these two oxygens are going to make a strong dipole in this direction, and that dipole isn't quite enough to steal that, to make that an ionic bond when this is a solid. But when you dissolve it in water, that hydrogen will now find its way to the negative side of a water molecule and get ripped right off. And that will leave an extra electron here, leaving this as negative, which will find the positive side of a water molecule and stick onto that. Does that make sense? So this isn't some random thing you have to memorize. There's a logic to it. It's a function of electronegativity. All right? So we'll say that. We'll say the electronegativity of the two oxygens provides the pull to ionize H to H plus. And we name it by just dropping the E like we always do from the parent alkane and adding oic acid. So methane would become methanoic acid. Ethane would become ethanoic acid. Propane would become propanoic acid. Butane would become butanoic acid, etc., etc. Would you like me to go all the way to dodeca?
Yes.
Dodecanoic acid. But anyway, so for example, let's draw, and we don't need a number locator because this can only happen on what carbon? The terminal carbon. That's right. In theory, I guess you, well, not just in theory, in practice, you can have more than one carboxylic acid on something. I'm thinking right now of citric acid, which I believe has 3. Now I'm going to check that structure to see if that's true. Citric acid certainly has more than 1. In my mind, it is 3, but it's a big molecule. It's a big kind of fancy molecule. Yeah, if you look here, double bond to O, OH, that is the structure there. That's a carboxylic acid. Double bond to O, bond to OH, that is another carboxylic acid. Double bond to O, bond to OH, that's another carboxylic acid. This, on the other hand, is what? That's just a hydroxyl group. Does that make sense? This would actually be very hard for us to name because we have functional groups on branches, right? Just one, but you've got, this is basically a 1, 2, 3, 4 carbon, so it's a butane. It's a dibutanoic acid. It's got 1 on each end, and then it's got a 2 carbon, an ethyl group that is itself an ethanoic acid functional group, and it's got a hydroxy group on there. It's got the alcohol. So this would be complicated to name. So it has a common name. We just call it citric acid. But this is what makes, citrus fruit taste all citrusy. You can buy this in powdered form. It's great for cleaning. It's a wonderful cleaning agent. Those 3 acid groups make it do an absolutely wonderful job. I use it to descale things. I pour a bit of it in my dishwasher and run a cycle. It does a much better job than the chemicals you buy just to, that are advertised as dishwasher cleaner. You can do the same with your washing machine, and they smell wonderful after. So, would recommend. Ethanoic acid, what's it going to look like? Yeah. Yep. 2 carbon chain, right? So carbon, carbon, and this carbon can just be connected to hydrogens, but the terminal carbon, in this case it doesn't matter which one you call the terminal carbon, will have what? A double bond to oxygen and an OH. Very good. And all together we call that a carboxylic acid. That functional group actually involves 3 bonds, right? And because it involves 3 bonds, it can only be on a terminal carbon, right? That is ethanoic acid. And again, this is the hydrogen that will get released when this is dissolved in water. Ethanoic acid is vinegar. So when you are consuming vinegar, it's just ethanoic acid, which you can see right there. What about this guy? How would we name this? Well, first of all, what's our main chain here? Careful. 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 1, 2, 3, 4, 5. There's our main chain, right? So it is how long? Pentane. So it's a pentane, right? And then what's our main functional group? Yeah, this is going to make it an oic acid, right? So this is a pentanoic acid. But then what else does it have? A methyl group on carbon 3. So what would the name of this be altogether? 3-methyl pentanoic acid. Bless you. 3-methyl pentanoic acid. Good. Yeah.
Would it still be considered an acid? Does the double bonded oxygen and the hydroxy have to be on the same carbon?
They have to be on the same carbon. Yeah. If this double bond oxygen were here, if it were a ketone next to an alcohol, that does not provide enough electronegative pull to acidify that hydrogen. They have to be on the same carbon. Good question. A very good question. So yeah, 3-methylpentanoic acid in this case. Now again, if you called this 3-ethyl butanoic acid, it wouldn't be wrong per se. It would still describe this structure. It would just be a worse name. Does that make sense? If you had identified that as the main chain, that's not as good a name, but it wouldn't be an incorrect name. It would just be a suboptimal name. It wouldn't be the most parsimonious name. I would mark it as not fully correct. But I wouldn't give you 0. I wouldn't make you my sworn enemy. I wouldn't refuse to speak to you ever again. One way to find out. Anyway, all right. By the way, for those of you in my biology class, there's a glaring problem with this question. Would somebody like to tell me what that is? Japanese honeybees are attracted to 3-hydroxyoctanoic acid, which is released by the orchid Cymbidium floribundum. But there's a problem with this question. What is it? First of all, we don't like this. Our chemistry people can know that. That should just be lowercase h. What else? Bio students? Is this how we write a binomial name? What should I have done? 2 options. Italicized or underlined. Good. So I feel shame about that. Shame on me. But I took this from the first half of a test question I gave a few years ago, because as any math teacher can tell you, kids relate more to math and science when it's real life, right? So here you go, real life. Japanese honeybees attracted to 3-hydroxyoctanoic acid, which is released by the orchid Cymbidium floribundum. So obviously I want you to draw 3-hydroxyoctanoic acid. Go for it. All right. Nobody's drawn it? Oh, I thought for sure someone would come draw it. All right, get up here. Get up here, you.
Can I tattletale Sarah? Just untied my shoelace.
You didn't wait for me to answer.
Excuse
No.
interruption. Could you please have Sarah come to guidance?
Oh. Wow, they heard the office heard. They're in trouble.
Yeah.
Functional groups always get numbering priority. So you're going to make your functional group numbers as low as you can, even if that makes your double bond numbers high. Good question.
Mr. Orlando, this is right.
That's great. The only thing I would say is, I love that you have an octanoic acid, but you started counting from the left. The problem with that is, what number would that make your functional group?
Oh, 5.
Even worse,
Oh.
8, right?
Would
Whereas
it?
what you're saying is the hydroxy should be
Oh, okay.
right? Yeah, so you never want to start counting on the opposite side of your carboxylic acid. You want to start counting at your carboxylic acid. So now that's perfect. Well done. That's great. How do we feel about that? Is that okay? Not so bad, right? I wanted to use this lesson to bring up one thing, which I believe I put a little baby bit of stoichiometry in your assignment. Did I? Am I right about that? Am I remembering correct? Just a little, right? Like just a wee little bit. Just a wee little bit. But, start remembering a little bit of that stoichiometry skill. I want to start dipping our toe in it now because it doesn't really become important until Unit 4. So I just want to make sure that by the time we get to Unit 4, we're kind of remembering that stoichiometry. Does that make sense? I probably won't even put this on a unit test, this unit. If I did, it might be like 1 or 2 marks. It's not going to be the bulk of it, but we're going to build up that strength so that by the time we need to use our stoichiometry again, that skill is kind of back in our heads and we remember how. Is that fair? So if you're looking at this today and going like, holy crap, I don't remember that, that's okay. Like you got time. But let's take a look. Let's do a little bit of stoichiometry. Can somebody really quickly remind me what stoichiometry is? Yeah.
It's like the equations we do to find out the weights and stuff.
Yeah, no, that's good. That's exactly right. Stoichiometry is just the ratios involved in chemical reactions. You guys don't even go remotely at the same time. Like both of those, she was like thing, and then you're just like, I guess I'll do this then. Yeah. And then you're just like, okay, well, I guess that's fair. That wasn't fair. Come on, like, good Lord, there was like a 3-second. She paused. She wrote in her head a little poem about beating you at rock, paper, scissors, and then like translated it into German, and then did the thing. And you're like, all right, I guess you win. Come on now, simultaneity or nothing. Anyway. So if we look here, how many grams of propanoic acid would be required to neutralize a 0.500 liter solution of 0.7 molar NaOH? Oh no! No, guys, this is actually easy. First things first, let's look at propanoic acid. What's that look like? Just real quick, propanoic acid, what's it look like? Prop means how many carbons? 3 is correct. Oic acid means that on the end we have and. Very good. That's making its 4 bonds. How many hydrogens does this need? 2. And this terminal one? Okay. What's the formula of this then? C3, H, 1, 2, 3, 4, 5, OOH. Sometimes you'll write it as C3H6O2. That's fine. This is actually the convention. You'll see this often. It tells us it's a carboxylic acid. You don't have to write it that way, but you'll often see it that way. Yeah. Now, if you wanted to call this C3O2H6, great. That's not wrong. This is kind of mixing a little bit of structure in with the formula. You'll see it very often because just at a glance, if you see OOH, then you know, oh, that's a carboxylic acid. Does that make sense? But you don't have to write it that way. Regardless, if we're going to do stoichiometry, what do we need to know about this? We could also, again, write this as C3H6O2, and that's totally fine, right? You'll even sometimes see it as C2H5COOH. You'll see lots of variations on it. Regardless, what do we need to know about it? How much it weighs. So let's look up the molar mass of this. We would call it the big M, if you remember, of C6H. Oh my. Okay, which sounds all complicated. If you don't remember this, or God forbid if you haven't studied this before, that's okay, it's not a big deal. It's just how much does this weigh? And if we look at the periodic table, we know how much one carbon weighs. How much does one carbon weigh? Should be 12.011, right? Okay, so we want to know how much 3 of them weighs. It's going to be 3 times that 12.011 grams in every mole, plus how many hydrogens do we have? 6 of them, and that should weigh 1.0079. 4 if you want it, yeah, sure, grams per mole. Sometimes you'll just write that as 1.001, or 1.01 rather, and I'm fine with that. I don't care, especially we've only got 3 decimal places here, right? So 1.008 would be fine. And then, what's oxygen? 15.9994 grams in a mole. And so just really quickly, that's 36 plus another 6 is 42, plus another 32, that should be 74?
74.079.
Great. So, 74.079?
Yep.
Great. Now, listen, again, if you haven't taken this before, or if that's stressing you out, I think I taught most of you grade 11 Chem, which is good. We don't need this skill to really be internalized until Unit 4, but if that's stressful to you, I can give you a copy of my old lesson on how to find molecular weight, and that's fine. But this tells us that for every mole, which is just a certain count of atoms, we'd expect this to weigh 74.079 grams, right? Okay, now, you're not going to need it, actually. We could, but it doesn't matter. Now, the reaction is just a 1-to-1 reaction, right? So that's the molar mass. That's great. And then the reaction itself is trivial. It is C3H6O2. This thing is going to react with sodium hydroxide, right? And it's going to produce water, right? And sodium stuck to this, missing one of its hydrogens. You don't need to worry about that. I'll give you the reaction for now, right? But basically, this is going to lose a hydrogen, right? And it's going to pick up the sodium, and the OH and the H will make H2O. Again, you don't need to be concerned about that for now, but that's just a classic acid-base neutralization, right? That actually goes back to grade 10 chemistry, right? Remember, we said that an acid plus a base gives us water, right? And a salt. You remember that? That's all this is. Same with organic acids, all right? Same thing. So now, the last thing we have to do is our little bit of stoichiometry. Does anyone remember the mathematical tool we use for that? Kind of. We do math with fractions and we work with units. We call it dimensional analysis. Do we remember that? Does that ring a bell? If it doesn't, again, you've got some time, and I will happily help work with you, like on this assignment, if you need a bit of help with the dimensional analysis. I'll help you with the dimensional analysis.
There was no dimensional analysis on this.
Oh, there wasn't, was there? Oh, but there will be on the next one. And again, just a little bit, just light. We just want to make sure that we're keeping that in our brains, because we're going to use it. So here, if you remember, we want to get our way to how many grams of the acid we need, right? And what do we know to begin with? Well, we have a volume and we have a concentration. If you remember from my dimensional analysis, I had a rule, which is if you want to end up with a fraction, start with a fraction. If you want to end up with not a fraction, start with not a fraction. We have 2 givens. Which one should I work with? We have 0.50 liters. That's the volume. And we have 0.75 molar, which is saying how many moles are in a... No. How many moles are in a liter? Oh, our chemistry is a little rusty. Our chemistry is a little rusty, team. That's okay. Grade 11 chemistry was a long time ago, right? that's okay. We'll bring it back. So we could start with either one of these and mathematically it would work. But to make our math easy, we want our answer to be in grams. Is that a fraction? No. So my rule is that in that case, which one of these should we start with? Not a fraction. The liters, right? So I'm going to start with a volume of base, right, in liters. And I want to work my way to grams of that acid, right? Well, how do you go from volume of one thing to grams of another? Well, what's our central unit? What do we always work in? Moles. So we're going to convert volume into moles of base, right? And how will we do that? Well, that's actually trivial to do because we know how many moles are in a liter. Specifically in this case, how many moles are in a liter?
0.7.
Yeah, we know there's 0.75 moles for every liter. So if we know how many liters we have, it's actually pretty trivial to figure out how many moles, right? That'll just be one step. And then once we know moles of one thing, how do we go to moles of something else? Where do we look? No. The periodic table doesn't know what we're doing. The periodic table, if I have 3.5 moles of sodium hydroxide, how many moles of... Yeah, it doesn't know. It doesn't care. But what does know? The chemical reaction, right? The chemical equation, the reaction, which in this case is a nice boring one, because what are all of the coefficients in this? What's the stoichiometry of this? One of these reacts with one of those to give us one of these and one of those. So you're never going to get a nicer reaction than that. All the numbers are just one. One of these, one of those, one of those, one of those. Does that make sense? All right. And then we have to go from moles of acid to grams of acid, and that is, of course, where we look at periodic table. We look at the molar mass, which we've already done, right? Now, again, I don't want you to stress out. If you're like, what am I doing with this? You got time. I just want to re-familiarize you with this because I don't want you to do grade 12 chemistry and forget grade 9 science or grade 10 science or grade 11 science. They all relate. In fact, I also don't want you to... Has anyone taken grade 12 bio in here yet already? Has anyone done it backwards? I don't want you to forget that either, because actually all the functional groups we're learning about here are the functional groups that you find in proteins and nucleic acids and in carbohydrates and sugars and all these things, right? So these things all interact with each other. If this feels new to you, don't worry, this isn't going to show up as like a whole bunch of marks in this unit, but it gives us a reminder of what we need to work on. So now we can do this math. We can start and we can say, okay, I have 0.500 liters of solution of the base. Nope. Yep, the base. Right? And what do I not want to talk about? What unit do I want to get rid of? Liters of base. Where am I going to put it? Great. Eventually, I want to get to grams of acid, but what do I have to go to next? Moles of base, right? And what's the relationship here? How many moles of base are in each liter in this case? Yeah, this is a 0.75 molar solution. So that means there's 0.75 moles of base in every 1 liter of solution. If I stopped calculating now, what would I know? Yeah, liters will cancel with liters. That would tell me how many moles of base I had. We could just do that math, but let's keep going. And again, I can't stress enough, you don't need to know how to do this today. So if you haven't seen this before, for God's sakes, don't panic. But do come talk to me and be like, hey, I haven't seen that before, and I'll give you a copy of that lesson, right? And we can show you that. I don't want to talk about moles of base. Where should I put it? On the bottom. Instead, what do I want to talk about? Well, I want to talk about grams of acid, but before I can talk about grams of acid, I need to talk about moles of acid. So I'm going to put that on top. Now again, if we want to look at that relationship, we would have to look at the balanced equation. This equation is really easy. In this equation, how many moles of base react? There's no number here, so what is it? 1. And how many moles of acid react? 1. So that's an easy one. If I were to stop calculating now, what would I know? How many moles of acid are going to be required for this reaction? But the question didn't ask about moles of acid, it asked about grams. So what do I put on the bottom of this fraction? Great, and what do I want on the top? Grams of acid. And we already looked up that number. How many grams are in a mole, or how many moles are in a gram?
74.07.
Great, does that number go on the top or the bottom? Yeah, because that's how many grams are in 1 mole. I'm working on, can I show you something I'm sort of excited about, though it's not quite working as well as I want it to eventually. Oh, shoot, what's this called again? Oh, I can't remember what I called it. Shoot. Anyway, I've made a dimensional analysis calculator. It's like 60% working, but if you you can't add with it yet. It just falls apart. It just goes crazy because adding with tracking units is actually kind of challenging.
Is it really a calculator then?
Yes. That's like saying if your calculator can't do logarithms, is it a calculator? Sure, it's just a calculator that isn't fully featured. Sure, but that's just a different mathematical operation, right?
That's like one of the main ones.
Sure. Logarithms aren't. Take physics. Sorry, I want you to know I'm aware that I'm difficult. It's been brought to my attention that I'm difficult, and I'm sorry. I'm not trying to be. It's just whatever. Whatever. It's what I am. What did I call this again? Oh, now I can't remember where I put it. That's very upsetting. Well, maybe I'll show you later. Well, see, I was all excited about this, and I can't remember what I called the. Well, we'll come back to it. You'd think, right? See, I thought it was in my practice app folder, but that's not there. I wonder if I deleted it. That's a distinct possibility. I didn't mean to delete it. I'm also just not good at naming things. I name things like, you get a lot of names with things like, oh no, dangerous, and things like that. Because that one, if you use that website, it just deletes everything. Oh, I feel so silly. Guys, I feel silly. That's how I feel right now. But that's okay. We'll come back. Yeah, we'll come back to it. That's okay. Anyway, and then we can just do this math, right? And the math is fairly trivial. 0.5 times 0.75. Well, that's just going to be 0.375, right? 0.375. And 0.375 times 74, well, that's going to be, glad you asked. This is going to be just shy of 30.
27.8.
Hey, okay. Yeah, exactly what I said. 27.8, right? And so we do our math here, and we end up with 27.8. Is that the correct number of sig figs?
No.
How many sig figs do we get here? 3 sig figs, right? How many sig figs do we get here? 2 sig figs. How many here?
5. Oh. Infinite.
Yeah, it's infinite, right? That's a counted number. That's infinite because it's a counted number. That's an infinite number because it's counted. This would be 5 sig figs. And this one is also infinite because it's definitional, right? 1 exactly. And which of these numbers do you have to go with then? The least of them, which means we have how many sig figs to work with? 2, which means our answer is 28 grams. Okay. Now listen, I can't stress enough that if that feels totally... one sec. What?
It's actually 27.7.
Okay. Thank you. Which rounds to? No, but you're good. I do appreciate the correction, but which rounds to 28? So that little bit of stoichiometry, I just want to remind you it exists. All right? that's what I want to do right now. I want to make sure you remember that it's a thing that exists. And if you need help with it, again, we're a couple of units away from it being part of our daily lives, but it is going to become a part of our daily lives again. So you could wait until it becomes a part of our daily lives, and then you could get all panicky and be like, oh my God, I don't know how to do this. Or you could look back at it once in a while now and get good at it so that when it becomes part of our daily lives, you're like, yeah, I got this. Which of those you do is up to you. But my advice would be remind yourself how stoichiometry works. You could always go back and look at your grade 11 notes. Oh, imagine that. Well, that's stupid, don't you think? In retrospect, that's a pretty dumb thing to do when you're planning to take grade 12 chemistry. So maybe you have a nice friend who would let you look at their grade 11 notes. Well, that's also pretty stupid, isn't it? That's called paying the stupid tax. So when other people who have their grade 11 notes get to Unit 4 and they know what they're doing, you can be like, oh, I guess I don't. That was silly. Next time, maybe I won't light all my stuff on fire. I still have my high school chemistry notes. Right? No, because I'm pretty good at this stuff now because I do it a lot. But you'd be amazed because the other reason you're stupid is because ask the people who've gone off to university and are taking first year chemistry, and half of them will tell you that they're actually studying their high school notes because they're a lot clearer and they're already there and they're nicely laid out and organized. And so for that stuff that in first year, you'll basically do grade 10, 11 chemistry, or grade 11 and grade 12 chemistry again, only at lightning speed, and then they'll throw some new stuff at you. And so, yeah, you're crazy to lose these notes because they are well laid out and organized and designed to teach you. And if you do take this stuff in university, it's not that it gets harder in university. It really doesn't. It's kind of the same stuff. Chemistry is chemistry. What it gets is faster, more intense, and more independent. There's more of a sense of you should be teaching yourself this. And so getting rid of resources is, I think, a poor idea. My first month at Eastdale, it was actually Thanksgiving because it was McMaster Reading Week of my first year here. So that'd be 9 years ago now. It was it would have been today. It would have been the first day of that reading week. And at the time I taught in Alaschuk's old room, which is now Ms. Treshik's room. And this girl came up to me and she was like, hey, you're Mr. Orlando, right? And I was new here. So I was like, yeah, I am. And I said, oh, what's your name? And she said, oh, I'm Vriddy. I said, oh, that's cool. And so we got chatting and she's like, yeah. And this was weird. This is not the kind of thing you want to hear. She's like, I'm at Mac. And I didn't realize. I assumed she was a high school student, but she was a university student back visiting. She's like, I'm at Mac. And then she said, yeah, it's neat to put a face to it because I listen to your lessons every day in my dorm room. And I was like, sorry, excuse me? But she was at Mac and she was struggling in her first year chemistry class. And a student of mine, this guy Kyle McGowan, who is a wonderful student and a great kid, had said oh, my high school teacher, this is back before most teachers, now there's so many online resources, right? But this is back before most people were posting videos online. He was like, oh, my high school chemistry teacher put all his lessons online. So she was running a study group where they were reteaching themselves grade 11 and grade 12 chemistry using my video. And she was here to visit her brother, Krish. And so she, anyway, that was weird. A weird occurrence. But yeah, I would never get rid of my high school science notes or math or anything like that, because if you do move on to upper ed, it'll be the same material, but faster and less organized. So it's nice to have something organized to hang on to. Anyway, I will commend this to your practice. You have an assignment due today. Make sure you get it into me. I'll tell you how I'm handling that one, which is unless you make some arrangement with me, unless there's some reason you can't have it done, I'm not asking you to turn it in. I'm just going to grade it what it looks like today. So if it's 2 questions done, then I'm marking those 2 questions and you just get 0 on the rest. Does that make sense? If you sort of come to me and plead your case, you could maybe plead your case to get an extension or whatever, but probably I'm going to say no, because what I want to do is tonight, mark them all and be done with it. Questions about that? All right. I'm going to see if I can find my stupid dimensional analysis calculator, which I'm quite proud of. It's very Desmos-y in its flow. You can just kind of type and the math happens.